Hi, my name's Scott Garrick. Today I'll be talking about current divider rule. The current divider rule is based off Kirchhoff's current law, KCL, which states that the algebraic sum of currents entering and leaving a network will equal zero. The definition above states that the total current at the start of a circuit will equal the total current at the end of a circuit, as current and energy must be conserved. In a series circuit, the current through each resistor will stay the same. The current divider rule only works in a parallel circuit, as the current needs to split between branches when it reaches a junction. Another word for a junction is a node. For a simple parallel junction, the general equation for current divider rule is Ix is equal to RT divided by Rx times by IT, where RT is the total resistance in the circuit, Rx is the resistance of that element, IT is the total current in the circuit, and Ix is the current of the element being found. There's one special case that applies to a parallel circuit which only has two branches of elements. This can be easily written and shown as IR1 is equal to I total times by R2 divided by R1 plus R2, and IR2 is equal to I total times by R1 divided by R1 plus R2, where IR1 is the current over R1 and IR2 is the current over R2. Do not discriminate against DC and AC current when it comes to current divider rule. They both are equal and deserve the same rights when applied in a circuit. The current divider rule is also used in other fundamental circuit equations and calculations like nodal analysis and calculating voltage and resistor values in a circuit. Here I'll show an example of using current divider rule. First, we need to calculate the total current in a circuit. We can use the equation V is equal to IR and rearrange it to get I is equal to V on R. This turns into 12 volts on 4 times 5, which is also divided by 4 plus 5 to equal a total of 5.4 amps in the circuit. We can now use our current divider equations. Therefore, IR1 will equal our current times by 5 divided by 4 plus 5, and IR2 will equal our current times by 4 on 4 plus 5 to get the result of IR1 is equal to 3 amps and IR2 is equal to 2.4 amps. To check if we have done it correctly, we can add up both of the currents found, in which this case it is true to equal the total current. I'd like to thank PowerPoint for helping me since kindergarten with presentations and helping me pass my subjects, and to the marker who has had to sit through my boring explanation of current divider rule. Thank you for watching.